Most students can write down the convolution integral, but don't understand what actually happens in the system. Two time variables, abstract symbols, and no physical meaning. In this lesson, we first visualize what convolution really does: mirroring, shifting, overlap. And only then work through it step by step. Once the picture is clear, the mathematics becomes intuitive. We have a dynamic system that is described by its transfer function g of s. We have an input signal u, which can be represented by discretization as a sequence of individual impulses. And this signal is convolved, represented by this symbol, with the system's impulse response function. How to derive the impulse response is something we already learned in a previous lesson. When we convolve these two signals, we obtain the system's response, generally denoted as y. Mathematically, it looks like this. We see that the response y of t consists of three components. First, the input signal u, then the impulse response function h, and then the integral. At first, this looks complicated and a bit confusing, I admit, because the equation contains two time variables, t and tau. Don't let that confuse you. It will become clearer in a moment. I will now do the following. I will simply swap t and tau. I do this so you can see that it really doesn't matter how we name the two variables. Both represent time, but we need a separate one for the shifting, meaning the overlap. Both versions are completely equivalent. Now we are also mathematically consistent, because you can see that after the integral we have dt, and on the x-axis of our signals we also use t, not tau. Now we will apply another little trick that again leads to an equivalent function. We simply move the tau minus t into the input signal u and keep h as h of t. This transformation is also equivalent and yields exactly the same result. With this last equation, I think we can understand and visualize the process much better. Now the next thing I want you to do is completely ignore the tau. Pretend it is not there. So now we have two components. We have u of minus t multiplied by h of t. What does that mean? We have u of t, our input signal, and u of minus t is simply the input signal mirrored across the y-axis. This mirrored signal, y of minus t, is what we convolve with h of t, the regular impulse response function. The third component is the integral over on dt. That means we are computing the area under the products of these two functions. As you know, an integral is always an area under a curve. When we multiply the two signals, we're looking at the area under the product of the two curves. And the process works as follows. Now the variable tau comes into play. Tau is the shifting variable. We have tau inside u of minus t, meaning that by increasing tau, we slide the mirrored input signal across h of t. After each step of tau, we evaluate how much the two signals overlap. So, tau moves forward. The signals overlap, and the area under the products of the signals becomes a scalar value. That value is written into y at tau, at the position corresponding to tau. it is simply the area under the products of the two curves. That is essentially the simplified description of the convolution integral. Strictly speaking, u and h are orthogonal to each other, and the area extends into the image plane, but this is almost impossible to visualize and usually causes confusion. Therefore, remember the following to understand the concept of convolution. First, one of the signals is mirrored. Wherever you see tau minus t, that signal is mirrored. Second, the two signals are slits over each other by letting the mirrored one run across the other as tau increases. Tau tells you how far the signals have been shifted relative to each other. And third, we compute the integral, meaning we evaluate the area of overlap of the two curves. That is the concepts of the convolution integral. This is a short extract from the full course, Fundamentals of Dynamics and Oscillations, including all derivations and exercises. The full version is linked below. Now let's visualize the whole process. At the top, in blue, you see the impulse response function. As the name suggests, it's the reaction of the system to an excitation of an unit impulse. Below that, you see the input signal, first as a dashed line showing the original signal, and then as a solid line showing the mirrored version, which has been reflected at the y-axis. And now, when we let tau move forwards, you can see how the impulse response function stays fixed, while the input signal moves along with tau and shifts across h. After each step of tau, the area under the two curves is evaluated. For space reasons, I've shown only the positive y half of the plot. Of course, the full signal of h is considered. Take your time to understand this. This is the essence of convolution. In the next step, I will show you, step by step, how the output signal y is obtained through the convolution. After understanding the principle of convolution and being able to visualize what is happening, I now want to go through a simple numerical example with you, step by step. Here we have an impulse response function, h of t, that I have chosen randomly. 5, 7, 9, 6, 3, and an excitation signal that has already been mirrored, meaning u of minus t. That means the actual input signal is 2, 4, 1, 3, 2, which simply results from discretizing a signal of this type. The first thing we can do is break our input signal into individual impulses. In fact, we can represent the input signal as follows. Each impulse is essentially a unit impulse scaled by its magnitude. At all other points it is zero, except where the impulse occurs. This is something we already looked at in a previous lesson. Now the variable tau comes into play. We move tau across the input signal in the order in which the impulses would hit the system. In this table, we enter the values that result from the equation. Since this is a discrete system, the integral is replaced by a summation sign. I chose this form of the equation because it's the most common in exercises and books. Since tau appears in h, we are technically shifting h of t by tau. Of course, it doesn't matter which signal is shifted over which. Now we start at the position y at t1. The system response at this point is the sum of all entries in the first column. So we shift tau by 1. This gives us u of 1 times h of 1 minus 1, meaning h of 0, which yields 2 times 0, since h is invalid for indices below 1. Then we shift tau one more step to the second position. We obtain u of 2 times h of 1 minus 2, meaning h of minus 1, which is 4 times 0, again because h would be evaluated at an invalid position. We fill in the entire column in this way and then move on to the next, and here things become more intuitive. We start in the first row with tau is equal to 1. U of 1 is equal to 2, and h of 2 minus 1 is h at the first time step is equal to 5. So the entry is 2 times 5. We repeat this for the entire column. Then we go ahead to the third column and again fill each row with the corresponding u of tau. I hope you already recognize the pattern. In the first row, we multiply by h of t minus tau with t, the third time step, minus tau, which is 1. So we get h at the second time step is equal to 7. Therefore, the first entry in the third column is 2 times 7. In the second row, we get 4 times h of 3 minus 2, which is h at the first time step, which is 5. So the second entry is 4 times 5, and so on. We fill the entire table according to this principle, and then we add everything column by column, exactly as the formula tells us. Add over all tau and multiply by the time step dt to determine the result at each time step. This yields the vector y, which defines the system response at every discrete time step, that is, in each column. Take a moment to think about this and try to recognize and interpret the underlying pattern. Did you notice something? The impulse response function shifts one time step to the right in every row. That makes sense because the impulses hit the system one after another, and therefore the second impulse produces a reaction one time step after the first impulse. And this reaction is, as the name says, the impulse response. In addition, it is scaled by the impulse's magnitudes. The impulse response is the reaction of a linear dynamic system to a unit impulse. That is why the response is scaled by the impulse's magnitudes. In this case, 2, 4, 1, 3, and 2. This creates a diagonal pattern because the impulses strike the system at different times. Imagine the system being hit by impulses, and delayed impulse responses occur, each scaled by the impulse height. For each time step, or each column, we then sum up the responses to the currents in all past impulses. This is nothing other than a superposition or the summation of system responses to time-shifted individual impulses. I hope this makes the concept and application of convolution clear to you. In the exercise section, we will apply this knowledge once again, using the example of a car driving over a bumpy road, and we will reinforce the material. Have fun with it.